So hello everyone. I'm Yan Yi, the host of. Hello everyone. I'm Yan Yi, the host of today's web seminar. So today we have two professors to give the talks, and the first talk is given by Professor Lee, and the title is Televerse Teleport to the Augmented Real World Driven by 3I Innovation. And so let me briefly introduce Professor Lee. Professor Tayan James TJ Lee is the Director of Computational Media Innovation Center, Associate Professor, Tenure Full Professor in U.S. System at Faculty of Engineering, co-founder of Computer Graphics degrees at the School of Engineering and Computer Science in Victoria University of Wellington, New Zealand, and the founder of the mixed reality startup DreamFlux. He worked in the immersive and interactive technology sector over 25 years across academia and industry. He worked at Samsung as their principal researcher and general manager to lead their computer graphics, medical physics research at Samsung Advanced Institute of Technology, and a senior researcher and senior manager of Research Innovation Center at Samsung Electronics. He served as the general chair for Pacific Graphics 2020 to 2021, XR chair for SIGGRAPH Asia 2018, and executive committee for AsiaGraphics Association. And so let's welcome Professor Reed to give the first talk.
Thank you for the nice introduction, Rangi. I will start to share my screen. Hope it's okay. Can you see my screen?
Yeah.
Okay, great. So kia ora, hello. My name is Tayan James. People call me TJ. Thank you for inviting me for I think this is the last AsiaGraphics webinar for this year. I live in Wellington, New Zealand, and now I'm currently in Seoul, Korea for my vacation. This would be my last talk of this year, and hope this talk would be ideal to wrapping up this year's talk. Today, I will introduce a new term, Televerse. This is our research framework as the future of metaverse for virtual teleportation and augmented telepresence. This term has been announced and introduced at SIGGRAPH Asia 2022 in Daegu a few days ago. And the core research in Televerse has three keywords: immersive, interactive, and intelligent. So I will skip this part because Rangi shared a great introduction for me. And as introduced from Professor Rangi, now I'm working as a Director of Computational Media Innovation Center. Shortly, we call it CIMIC. So our vision is to be a global hub for digital media frontier, and we work for future targeted research, stay beyond the cutting edge at the immersive, interactive, and intelligent technology, or start with I, so we call it 3I and 3I axis. And we also develop a pipeline to transfer research impact to the industry value. So our current research is in three research teams: augmented telepresence, we name it a Televerse, and digital twin, and AI effect. I will introduce our research in augmented telepresence and a little bit about the AI effect today. I will start with a short concept video to showcase the Televerse concept. Yeah, this is concept video, and the actor our student and researcher, not a professional actor. I hope you enjoyed it. Okay, what is a televerse? Televerse is not a virtual world. This is a real world where we live, and televerse is a actually digital copy and twin clone of our real environment. So people can virtually teleport to and from anywhere in the world. Their telepresence is augmented by digital information in televerse, as like a visual effect movie. Why the televerse is matter? The current metaverse is to meet in the virtual world as avatar, but televerse, we can meet in the real world created by real-time 3D capturing, modeling, and streaming. And in the media technology point of view, I feel the current metaverse has been advanced from the animated film, such as Toy Story, because this is fully virtual storytelling with CG creature in CG world. And movie is for recorded media, so no interaction with linear storytelling, but metaverse is different because it's an interactive online media platform. So we can build a story in live with connected people. But how about televerse? I feel televerse can be a real-time live framework advanced from the movie visual effect pipeline. In movie visual effect film, we capture real-world live action, then blend virtual object for creative storytelling. So our high-level strategy to realize the televerse is to transform the offline movie visual effect pipeline into real-time live platform and connect it with social network platform like Metaverse. So I'll talk a little bit about the visual effect pipeline. This is a part of the behind the movie scene of Hobbit from the FX guide. In this scene, we have an actor and a 3D troll. The actor is in the studio set, and the troll is the digital world as the 3D virtual creature. But after having proper lighting, rendering, and blending, virtual and real are co-presented in the Middle Earth. If we have fully immersed in the movie, we also feel telepresence in the story. So for making the nice visual effect and the high fidelity mixed reality scene, there are several technical challenges. And film we use rendering techniques such as ray tracing and path tracing. And this algorithm is based on the light transport simulation. And when we have an intersection point of each ray with the scene, we evaluate the rendering equation to compute the color of the intersection point. In particular, for seamless blending, we need to use the real-world light. We use computer vision method to extract light information and render the scene with image-based lighting. And then finally, we blend the rendering into the real-world background. But augmented telepresence require real-time visual effect. So we need to have two keywords, immersive and interactive. This is an example of telepresence with 360-degree video. It enables a wide field of regard and telepresence at the captured spot, but the interaction is quite limited. This is augmented version of 360 video for augmented telepresence. As you can see, we have real-time blending of 3D asset. Using the consistent lighting, shadowing, and realistic rendering and composition, people can have illusion to play with scene object in their telepresence. So our high-level strategy, as I mentioned that before, is to realize televerse is to transform the movie visual effect pipeline into attractive media platform. So actually, the place that I'm living is quite ideal for doing this. So Wellingtonians contributed 50% top 10 highest grossing film in the global movie sector. I think it might be 60% soon. Contributed because the current Avatar is quite popular. So Avatar 2 and Avatar 3 and Avatar 4 is coming, the percentage can be larger. This is based on the Oscar-winning visual effects company in New Zealand, which is Weta Digital, Weta FX, and Weta Workshop. Especially in New Zealand, movie industry is specialized for visual effect, which can augment a live action film captured from the real world footage with seamless blending and computer generated imagery. So live visual effect has extra challenges because we need to have whole real-time pipeline for entire visual effects pipeline. And also we need to have automatic solution to remove any manual tuning. And we wanted to have immersive solution for high fidelity final output. And there are many challenges, and this is a good topic for research. So the first thing that we use for the real-time performance is to optimize the resource and computation for human visual system. We try to find the perceptual threshold to optimize resources and computation for human visual system. For example, after a series of the perceptual user studies, we observed that human eyes are not sensitive to perceive composition abnormality, although we reduce the size of light map. So we could reduce resolution of the light map almost 90% compared with a typical visual effects studio setup. But people could not find the abnormality in our user study. So based on this finding, we optimized the image-based lighting. And based on result, we produced almost over 500 frame images per second with various roughness level and lighting condition. And we can use it for a real-time version of the image-based lighting. So we integrated our image-based lighting into the Unreal Engine and Unity as the plugin. And then we added a module to detect dominant light to cast the shadow. And finally, we blend the rendering into the background of real footage. So we adopted Paul Debevec's differential rendering algorithm into 360 video setup. And then finally, we integrated the whole process into a unified framework called MR360. It can be regarded as a compact visual effect pipeline for real-time processing, including lighting, rendering, and composition done automatically. This is an example of MR360. MR360 provides an easy toolkit for content creation. So lighting and shadowing are automatically adjusted. So content creator can easily drag and drop the 3D asset to blend them into 360 video. This is an example of our live demo of augmented telepresence made by MR360 Toolkit. People can virtually teleport to Wellington Civic Square and play with fish. So this is a kind of a experience that they cannot have the real world, but they can do in the televerse. So I covered two keywords so far, immersive and interactive, and I wanted to add one more keyword, intelligent, for providing the more intelligent, smart solution for televerse. So as I mentioned, the rendering is a process to produce images from the given 3D scene in computer graphics. The inverse rendering is the opposite process. Given an image, we extract scene information such as camera information, light, and texture and geometry from the real world. The inverse rendering is, I think, it's a kind of overlapping area between computer graphics and computer vision. And in this talk, I will focus inverse lighting, which is quite specialized for the visual effect. So we construct a real world surrounding light from the limited input is called inverse lighting. For high fidelity augmented reality, we need to estimate 360 surrounding light as a radius map of the real world from the conventional photograph took from the mobile phone, for example. So we try to solve this using convolutional neural network. So our method is to train convolutional neural network to learn relationship between the input as the partial view image, like a picture from mobile phone, and the output as the 360 radiance map, like environment map. Especially our method is to estimate reflection maps, which can cover the material variation in different roughness level, as well as the light information like radiance map. So we train neural network for the diffuse reflection map first, and progressively advance the network to estimate mirror-like reflection map. We implemented it using a stack CNN. So train the diffuse reflection map using CNN, then transfer the learned weight to the next CNN. Then we keep doing it until training the CNN to predict mirror-like roughness level. So this progressive scheme provides a good initialization for each reflection and also improve the overall quality. This is a result. Left is the input partial wave image we can take from a mobile phone, and from the top, ground truth, our method, result of our method, and the previous state of art. So as you can see, the estimation result is a little bit blurry compared with the ground truth, but it was quite efficient to produce surrounding light for image-based rendering, image-based lighting. And this is another outdoor example. It also provides a plausible output for the image-based lighting. Especially the indoor is very challenging, but the neural network can learn the relation very efficiently to have a dominant light position and then overall tone quite fit to the rendering. And so even the indoor scene, it shows a very promising result. But however, the light estimation based on machine learning mostly rely on their training set. So it has limitation to adapt input variations such as field of view changes, resolution difference, and exposure and white balance setting. So everything is slightly different in each mobile phone. So we developed a DLNet, dynamic lighting network, to provide a robust light estimation from input variations. So we have a Beijing network with an autoencoder and decoder. Then we add our spherical dynamic filtering framework to generate convolutional filter for input variation. So I will skip the detail for the technical part today. The detail can be covered in our paper. And this is our result in a mobile setup. As you can see, our DLNet estimates surrounding light with a variance of field of view and exposure in this demo. Okay, so we talk about the estimating light. So I will change the topic a little bit for the relighting to lighting. So especially portrait relighting emphasize on adding novel lighting information to the portrait picture. But if the input has extreme lighting conditions such as hard shadow and high highlight, the existing solution causes artifact. So removing undesirable lighting is important for relighting, but this is a more fundamental issue for computer vision beyond the relighting applications such as detection and segmentation and tracking. But delighting from human portrait image has extra challenge because we might have a glass, we have hair, we have clothes, so there's more variation than face. So we developed a solution for delighting of a human portrait image using deep neural network. Our base architecture for portrait delighting is UNet, and we added a second decoder to learn an offset image. The offset image is the difference between the relight and delight image. It actually contributes to separate the shading and texture in the encoder for more robust delighting outcome. So we use an offset image and also add a soft shading image and high frequency mask for our final solution. And this is our final result for our portrait image delighting.
We present some of our delighting results, showing consistency under a wide range of illuminations. against the state of the art, if it is more robust to challenging shading features such as shadow borders and reflections. Here we show some examples of delighting in the wild images found on the internet. Notice the removal of shadows and the removal of reflection. We present some.
Okay. So we covered the lighting issue, but at this point, there might be some questions. So our method will start with 360 video background, and also we cover some method to overcome the 360 limit with mobile phone using image of mobile phone for estimating light. But if the background is 360 video, so the movement during the teleportation is quite limited. We just can rotate our head. So how to move around when teleported is kind of a fundamental issue to solve. So one of the solutions is to jump around capturing spot like a Google Street View in one 360 video to the other 360 video. But the other solution is to freely walk around with panoramic scene. So let's talk about how to work around with panoramic view. So walk around with panoramic view requires 6 degrees of freedom movement, including 4 3D rotation and 3D translation. So we recently presented a volumetric panorama solution for 6-stop navigation. So our method is especially designed for capturing the large space. We use a single handheld 360-degree RGB camera, and then we just can walk around because it's handheld camera to capture a large space. So while the video recording is turned on. And then we capture some spot and estimate the depth using the structure from motion. And then we synthesize novel panoramic view in real time for 6-stop navigation. So I will skip the detail of each step, but I will show the final result for 6-stop navigation and how to capture the scene with our method.
We unlock freedom of movement in video using our volumetric panorama solution. Users can freely move away from the pre-recorded camera position, exploring the environment as if they were there walking around. 360-degree videos provide users the ability to immerse themselves in environments. Users can freely look around, but cannot walk away from the camera position. While we could move the 360 camera through the environment during the recording phase, users will still be locked to the pre-recorded camera path. Here, we can enable our volumetric solution running in real time, breaking away from the pre-recorded camera path indicated by the spheres. Here's another example of an office. Let's move our camera to an extremely far away position to show the volume of our solution. As you can see, this will allow users the ability to freely explore the environment with both head rotation and movement. Simply capture a video of the surrounding environment using a conventional 360-degree camera. After capturing, we can explore the office with full freedom of movement. This includes walking and looking around in all directions. We support casual and accessible handheld cameras, selfie sticks, and tripods to capture environments beyond the room scale. Users can freely explore large-scale environments. They can even explore large outdoor environments, such as an entire park.
So this demo was captured from our version integrated Unity. So we covered some technology for immersive and intelligent and interactive keyword. And now it's time to discuss how to merge these 3 keywords, immersive and interactive intelligent solution into the interactive system. Especially to enable remote communication and collaboration to connect people in Televerse. This is another concept video for remote workspace using augmented telepresence in Televerse concept.
Imagine being able to appear next to someone the moment they need help. A business's success is driven by the skills and actions of its employees. But to work effectively, they need to be able to communicate easily and accurately. Some problems require complex hands-on problem solving and are ill-suited for video calls. When employees face a difficult problem, they need to be able to ask for help, even if those people aren't nearby. That's why we created AVT. Now you can really be where you are needed. Move around with total independence, view from any angle you want, and use augmented reality tools for maximum effectiveness. Using virtual teleportation, you can contribute to solving problems as if you were really there. Upgrade the way your team collaborates and allow them to work at their full potential.
So in this concept video, we use asymmetric setup. What that means, in the video, the remote people who teleport to the working site wear the VR headset to have immersive telepresence at the remote work site. On the other hand, the local people who are already in the work site wear the AR goggle, see-through display, and they see the avatar of a remote person, and then they have a face-to-face communication. So this is a mixture of augmented AR setup and VR setup in the mixed reality environment. So this is a captured live demo, not a concept video, from the local host view. The yellow avatar here is the teleporter from the remote space, and the local host and the teleporter communicate face-to-face and collaborate the mixed reality space. And this is another example of remote training. Remote engineer can guide the student to fix the lab equipment. Collaborator can use various visual cues for better face-to-face communication, such as the digital twin of the lab equipment and pointer and gesture to the avatar. So this is a working version of the demo. And now, so it's time to discuss how we can apply this kind of technology and system to the actual application. The actually application area of the Televerse and augmented telepresence is very wide. So it can be different in each country and in industry sector. But I would like to introduce few application areas that we identified in New Zealand. The first application area is the live event. But in the live event, there are a few subclasses. One is to broadcast live event to remote audience. The other is to allow remote performer to be in the live stage. And the final is to provide a mutual communication between people at the event and the one in the remote. In AsiaGraphics and AsiaGraphics Asia, our team presented several live demo in the real-time live and via AR event. I will shortly share a part of a video for our virtual booth presentation in the real-time live AsiaGraphics 2018.
Awesome. So you can see that it's as though I'm in the virtual booth with Steven and Lohit. So looking at the booth right now, it's a little bit empty, so what I'm going to do is add a few objects to kind of add to my video. So we're going to have a table, we're going to have a chair, we're going to have a little real-time live object, and some plastic materials. Oh yes, and also we need a banner, and special thanks to our sponsors, Samsung and NVIDIA, for helping us out. So you can see that it doesn't look too bad. With our lighting solution, we're able to naturally blend digital objects into the video. And so as a designer, it's really easy for me to more accurately pre-visualize what I'm trying to do, along as as well as keeping immersed in my task. So obviously this is a virtual booth, so we don't have to stick to regular objects. What we can also do is add something more interesting. So we've traveled all the way here from New Zealand, so it would be a shame if we didn't bring some New Zealand flair over here. So I'm gonna add a couple of, ferns to the scene. Awesome. Got a log. Ooh. Yeah. And of course we need a booth mascot, so here's a kiwi bird. Awesome. Okay, so basic layout is done. I'm quite happy.
And recently we tested our asymmetric framework for the live concert in Auckland, New Zealand. We developed a system called the Telefest. Telefest allow multiple 360 live input and control, and provides an easy tool to blend a virtual asset for real-time visual effect. Then the system can stream the augmented 360 video channel to internet. So we applied our Telefest into the K Festival in 2020, a hybrid concert at the auditorium in Auckland, New Zealand. And K Festival hosted a couple of thousands of in-person audience, as well as a 2,000 online audience. We set up 3 live streaming 360-degree cameras at the stage left, right, and the middle of the crowd. And at the concert, we added a live visual effect and streamed 4 360 video signal to YouTube 360 channel. This is example of the remote audience view. As shown in the right, we added a tiger on the stage next to the performer. Even we filled the auditorium with the water and float the turtle ship. And this is a video of on-site producer view that I captured. So the other important application in New Zealand is tourism. This is our early stage case study in 2017 for virtual tour. People sit in the tri-show in the image with VR headset and control at the Wellington Airport. Then they can virtually visit to the destination of Singapore Airlines and experience the local culture with augmented telepresence at the visiting site. So the original installation at the Wellington Airport was supposed to be a few weeks, but was extended for 3 months by the request. And we opened the demo to the public for 3 months, 8 hours per day. And for 3 months, we had no technical fault at all. And today I will show you the very last demo of our team for this year. It was SIGGRAPH Asia Daegu happened a few weeks ago. And this was a real-time live video capture from our team. So if you missed the chance to see the real-time live demo, so this is a time that you can enjoy the real-time live of SIGGRAPH Asia this year. I will turn the video and hope you to enjoy it.
On stage we have a 360 camera live streaming. That's you right now. Yeah, there you go. Hello. Yeah, there's you. And on stage we have Warren Butcher. We've augmented a meteorite orbiting around him. And as you can see, it not only goes in front of him, but it also goes behind him. We've got this mutual occlusion happening. Go around one more time. And if I drop that in front of him, he can also push it along using natural hand gestures. So there's a sense of occlusion and collision detection between the real and virtual worlds. So how do we do this? Firstly, on stage, we have a live streaming 360 camera mounted with a LiDAR sensor providing a point cloud. This is live streamed over the network and into a game engine. Here is the point cloud information projected onto a 360 panorama. You can probably spot Warren somewhere in there. There's one right there waving. All right, so we can't use this directly. There's plenty of holes through it. And for mixed reality, we need to fill that in. So the first thing we do is a few steps where we densify the depth map, fill in the missing holes, It's a little bit noisy, so we add a few post-processing steps to smooth out the edges, add a ceiling and floor to the depth map, and now this is ready to use for compositing. We can put virtual objects behind and in front of real objects. For collision detection, we need a geometric representation with a mesh. This is the auditorium right now. We achieve this by first putting a spherical primitive in the center of the scene and distorting each vertex based on that depth map. This is the result you see now. All right, so that's how we do it. Let's show an example of using this. I want to switch over to a different perspective. The idea is telepresence, so I want to set up a producer and perform a scenario where I, the producer, am going to be remotely located, and Warren is going to be locally located with the 360 camera. You, the audience, could imagine you're like a participant that could be online, anywhere in the world, viewing this in real time. All right, so let's get rid of the rocks. We could augment this scene with a bit more interesting content. How about some snow? It is winter time, after all. We could add some snow coverage. As you can see, you're in the snow. It's going up and down the aisles, in between the chairs. We've got a nice geometric representation of the real world, and it's quite fun. Hope you're not too cold out there. Warren's getting a bit cold, so he's put on his hoodie. All right, now we can do collision detection as well, so let's give him something to interact with. Why don't you give those a little push, Warren? So let's decorate the environment a little. It's looking a little festive. Maybe a little Christmas tree over there. Fireplace, it's looking beautiful now. Although the snowman's hat is a little boring in my opinion. Could you make that a bit more interesting? Okay. Oh, the snowman doesn't seem to like that. You're not going to hit it, are you? Oh, Warren! That's not very nice. Let me rebuild that. Alright, well I'll let you two sort it out. Say goodbye now. Alright, that concludes our first demo.
Yeah, actually, this demo is the right timing to see today. This is just one day before the Christmas Eve. I hope you enjoyed it. So this is what I prepared today. I hope you to enjoy the talk and then enjoy the video that I share for some demo. Today I introduced a new term televerse and then the augmented telepresence, and then have some discussion for the live visual effect pipeline, and especially for inverse lighting for solving the problem for light estimation using deep neural network. And then we discussed a kind of method to merge this like immersive, interactive, intelligent keyword together for a symmetric telecommunication framework. And then finally introduces a few applications and then case study that we have done so far. These are the list of references for my talk today, and hope we can work together, because work together we can make the change. I hope we can build the televerse together. Thank you. Thank you for inviting me, and thank you for having share your time to watching this talk today. Thank you.
Thank you very much, Professor Lee. Thank you for your wonderful speech. And so now the audience can ask questions. Actually, I have some questions. So yeah. In the live demo you show at the last, so what kind of device does this technique need?
So we have live capturing at the stage, and in order to do that, we have mixture of the two capturing setup. We have live 360 RGB capturing, and also we have LiDAR sensor, which can have panoramic depth. We can have 10 frames per second for the depth image of the environment, and then we merge it together to give the RGBD images for live feed. With using this RGBD information of the surrounding information, we can have occlusion handling and collision detection, so we can have some novel interactive effect in the live show.
Okay, thank you. And so that this technology will be extended to like mobile device that our day people can use.
Yeah, I think the hardware technology is rapidly improving. So currently we have many camera in our phone. At some point, probably, and as you can see in the some 360 camera is very lightweight and a very small form factor. So I think it's possible to integrate 360 sensor into mobile phone in near future. And many phone also have the depth sensor already. So I think that kind of a thing can be done in near future, probably hopefully within 5 years, 10 years. That's my expectation, but I don't know. Let's see.
Okay.
Hi, Ryan. Yeah, this is Li Kang. So can I ask a couple of questions for James? Okay. Hi, James. Yeah, this is Li Kang. So very nice. Yeah, you have offered a very nice talk. Just before the Christmas Eve, just you mentioned that I believe that your talk is the last one in this year's AsiaGraphics webinar. Okay, it's amazing that you showed a real-time live demo at the SIGGRAPH Asia this year, right? Just 2 weeks ago, I think.
Yes, just 2 weeks ago. Yeah.
Okay, so you mentioned that you are still in Korea. Okay,
yeah, I'm still in Korea. Yes.
Okay, yes, that's great. Okay, so I have a couple of questions for you. Yeah, maybe one is more high level. So you mentioned the Televerse and the Metaverse. So are these the same concepts, or do you think there are some difference between the two concepts?
So metaverse is actually, there are lots of definition, and there's a wide definition and then focus definition. But even the wide definition is possible. The current metaverse platform is mostly focusing on the virtual world. Mm-hmm. So we, so like Roblox and then Fortnite. So we can meet in the virtual space. This is good. So we have social networking in the safe virtual space, but this can have some side effect to isolate us with real world environment. So the Televerse is more like a advancement of telephone, television, and the teleconference, and then the Televerse is more like a social platform of future of teleconference. So like a similar concept, but the root might be a little bit different. So the base of Televerse is a real world, not virtual world. So we wanted to be based on the real world where we live, and we wanted to add information like augmented reality. But this is in the Televerse, we are going to the other place. So this is not the place that we are living, we are staying. So this is other place that we have telepresence. So the thing that we do is augmented telepresence. So the basic thing for the Televerse is augmented telepresence. So this is slightly different than metaverse that we are currently focusing on, because the metaverse is for virtual space, but Televerse is for real space. I think that's a fundamental difference between metaverse and Televerse.
Okay,
based on my definition. Yeah.
Okay. Yeah. It's good. Okay. So in Televerse, so for the applications in mixed reality, you have to estimate the lighting condition and also to estimate the three-dimensional space for the fundamental step, right? Okay. So you mentioned the work that you use CM to estimate the light map. Yeah, for the outside scene, right? So I'm not sure whether this method work for the indoor scenes, because the lighting is not directional lighting, but they may have some many lighting or or some not indirect lighting conditions. So can you give more comments on this work?
Yes, the radiance map that is used in the film doesn't have that information, but they have as you mentioned, that direct lighting. But in cases at the moment, they are using radiance map, and then they regard it as like an infinite distance, like a directional light. But this is a conventional setup for rendering in the film industry. But as you mentioned, that there's a limitation because there's no depth information, location information in 3D. So that need to be improved. But the current setup is based on the directional light. And our method is also provide for estimation of the indoor scene. But as you mentioned, that there's a limitation. This is we assume that this is far away. But when we have a test in the rendering, this is quite work well compared with abstract light that have only just one directional light and the one abstract light. Compared with that setup, the radiance map itself was more providing more reliable lighting information for indoor scene as well.
Okay. So thank you. Yeah, maybe due to time limit, I have one very short question. So, you mentioned the inverse rendering as well. So the task of the inverse rendering to estimate all the three-dimensional information from the environment, right? So 2 years ago, there's a very hot topic about NERF, implicit representation. Okay, I believe you have almost aware of that. So what's your opinion about the NERF and the transitional mesh representation? So just some quick comments is okay.
Yes, so the NERF is good to reconstruct 3D setup, 3D information. But the thing that we try to is to capture the large environment. Yep. So in order to do that, we have a 360 setup. It's like an in and out capture. Usually NERF is out and in capture. So we have large number of the overlapping information for NERF, but 360 setup is limitation for that. So there might be some advancement of NERF for adapting the panoramic setup. So this is a thing that we are currently working on. And I believe that combination of the 360 and the NERF can have some of a solution for capturing the large environment, but this is a still ongoing research from our team.
Okay. So I think I have to stop now. Okay, thank you very much.
Thank you.
Thank you, Professor Liu and Professor Ri. And next, I will introduce the second talker. I will first show the screen.
Okay, should I start sharing my screen?
I will quickly introduce for a second. And so the second talk, the title is Capturing and Display 3D Avatars in Immersive Environment. And the speaker is Professor Ye Pan. Professor Ye Pan is an associate professor at Shanghai Jiao Tong University, where she leads a character lab and focuses on using virtual environments and computer graphics technologies to advance character animation and avatar performance, and thus improve user experience. She previously worked at Disney Research, Los Angeles, and received Master and PhD in Computer Science from University College London. She has served as Associate Editor of the International Journal of Human-Computer Studies and a regular member of IEEE Virtual Reality Program Committees. And let's welcome Professor Pan to give the second talk.
Okay, cool. Thank you very much for this opportunity. So I'm going to share my screen. Okay. It looks like my camera is not working, but anyway. So Is everything? I think everything is set up. So I'm going to talk about the avatars and characters in today's talk. So in today's talk, I basically divided my talk into two parts. The first part, I'm going to talk about how to create characters and animate it. And the second part is how to display it on the 3D displays in the virtual environment. So here's my brief introduction. You probably already heard. So let's go to the next page. So the first thing is why we're doing it. There was a lot of the characters in our life, like we meet the stylized characters, we meet the human beings in the virtual environment. So when we're in the 3D environment, we will interact with the humans and the characters and different kind of creatures. And in my research, I'm particularly interested in the stylized characters. So a very big background. So motion capture. To creating the characters, we all know that we use motion captures like putting a lot of markers on the people's face and then or put a lot of markers on people's body as well. But we all have noticed there was a problem is that when we capture human beings and they cannot express that exaggerated expressions as the stylized characters. For example, if you open your mouth very large, there was a limitation for you human beings' mouth. However, for the stylized characters, you can open as much as you want. That is the problem that we're going to solve for capturing characters. First, I'll give you an example. For example, like if you can see the first slide was a lot of the human beings' face, like in the different expressions. If we use the nowadays motion capture software, like the AI kit or the from the like the iPhone, or you will use the faceware on the Windows PC to capture the human face, we can only capture the geometry features, but we cannot express character very expressively with like artist created characters. So we developed a method to overcome this problem in order to making the character very, very expressive. Like the last 4 lines are example of the creating the stylized characters. You can see on the faceware there was no expression basically, even though it's geometrically very matched. However, for the last couple of the characters we created, you can see very expressive one. Okay, I'm going to talk about how we create this. First of all, we created we use a deep learning method to finding a match of the expressions, and we divided expressions into 7 categories so that we can get the emotion matched, and then we use the geometry match method to adding a layer on the blend shape animations, and then finally we extend it to the multiple characters. And the basic idea is adding a machine learning model on top of the traditional motion like blend shape animation pipeline. Like the top lines are blend shape animation pipelines, and then the second the last 2 lines is a tool model for integrating machine learnings. Here is examples is how we created like the character. This is the motion capture combined with our method is like this.
So Yapan, do you have audio for this video? So
yes, it was audio. Oh, you cannot hear the audio?
Yeah, maybe you have to set.
Okay.
Set up
okay.
Time. Okay.
Okay.
So go ahead. Go ahead.
Okay, I will just talk through this audio so that people can understand what's actually going on. And so this is actually the audio that express that the character can express their facial expression based on our models. Instead of just giving a geometry models, right, we adding emotion features. This is one of the example. So how, in summary, how we're doing this is we use the traditional blend shape animation techniques and adding on the machine learning models so that we created the first real-time system that transfers the human facial expression to the multiple stylized characters. It's not only geometry matched, but also perceptually correct. So this is the first thing that I would like to introduce is our system is makes the blend shape animation techniques better. And as we know that motion capture is one of the methods to creating the animations. Another method is completely based on the machine learning technology. So on this one is we created the completely audio-based animation techniques. But before that, we created a data set. We got lots of the animation clips from the movies and from the 3D animations, and we collect all of them. And there was some problem with creating this. The first one is that the majority of the data set is on 2D faces, but our data set is for the 3Ds. A couple of them is we created from the 3D animations, and a couple of them is we generated from 2D animation and map it to the 3Ds. Once we got this data set, we created like the emotional voice puppetry. This is completely based on the audio input and makes the character talking. We can apply this to the virtual reality system and some like the phone app as well. The reason for us to do it is in the virtual reality, when people are wearing the headset, we cannot see our face anymore. We can only see we cannot see our eyes, and the face is very difficult to capture. So the audio-driven system is very important in such a system. So based on this data set, we created the audio-driven animation generation method so that people in the VR can animate characters. So up to now, we introduced the two methods. The first one is we optimize the motion capture method. The second one is we completely use the machine learning technology to creating animation. And last one, I'm going to talk about to creating the virtual reality film that's using keyframe animation. This is light up with the 3 types of animation pipelines. For example, using keyframe completely machine learning, and now we apply this to the virtual reality film. How we're doing is this work is actually be used in the Cycle and the Frozen 2 filmmaking system. The problem is like this, why we're doing it. The traditional way to creating the animation is very, very difficult, that people have to rotate the characters so that make sure the angle is correct all the time in Maya, that using the mouse and a desktop interface. And our method is apply this using the virtual reality system. Another background is how the traditional film is made, is that people using a camera to capture the one shoot and rotate around the camera so that it makes sure that all the angle was correct. Here example is how we import this like traditional keyframe animation into the motion, into the virtual reality. However, they have a problem is that only the one of the person can say this. This is our first generation of the character posing software. And our second software is second version is allows multiple person to animate the characters in the virtual reality. Here is an example how people actually working on it. It's like a 2-person was actually interact and creating character together. And here example is how we're doing the forward kinematics and the inverse kinematics, and also how we scale the character larger or smaller. And it's our interface. And it's not only support keyframe animation, but it's also support the motion path editing. And this was developed on the Unity and based on the Photon software, so it can extend to the multiple clients. As examples for the collaborating, animating, editing examples. So in summary, that we the last way of creating animation is creating using keyframe animation, but different from the traditional keyframe animation is we import this to the virtual environment. So takeaway from home. For the capture characters, like today, I introduced the 3 new ways to creating animations. The first one is adding machine learning model on the blend shape animation. The second one is completely audio-driven animation. It's first we create a data set, and then we generate animations completely based on machine learning for 3D stylized character. Instead of the videos, it was lots of paperwork on the 2D character, but we didn't see much on for the stylized characters. Okay, next I'm going to move to how can we display those characters. Once we get the character captured and we want to display nicely, and because it's a lot of the human factor was influenced by those ways. The first one is eye gaze, and also interpersonal trust, and physical embodiment, leadership effect, and the engagement. So for big background, it's as everyone can see on this Mona Lisa's like smile, you can see if you rotate around your head left or right, you always feel like the Mona Lisa is looking at you. So the problem for this one is all the 3D image that printed on the 2D surface, the sum of the like spatial clue was getting lost. That is why when you rotate around our multiple person in the room, all of them will feel like the Mona Lisa is looking at you. And also if you look at the right picture, there was Uncle Sam pointing to you. No matter where you're standing inside a room, you always feel like he's actually pointing at you. So that is a huge problem for the teleconferencing. But it's not a problem for the virtual reality. So that is the more the fundamental motivation we're doing it. This is a very big project that collaborates with a lot of universities that is capture one person and then display this person in another location. It's like a telepresence. First, I'm going to introduce the 4 telepresence mixed reality displays that have been built. The first one is a spherical display, and it's supporting like the eye gaze. The reason for this spherical display is it's not only look like the human head, but also like this, if you're situated in the room, everybody around the room can see it, not like the 2D display, only the person in front can see it. And this is similar for the cylindrical display. And the reason for we developed this is supporting multiple users. And next one, I'm going to talk about a random hole display. This is similar to the parallax barrier 3D display, but different from that is we randomize those barriers so that multiple persons at arbitrary location can see it. And last one is I'm going to talk about how can we presenting an avatar on a spherical display. Here's the features we developed comparing to the flat display. The first one is we capture a person with multiple cameras and stream those videos onto another location, and finally using the computer graphic techniques to present this on the spherical display. This is how we do it. It's quite straightforward. First, we use capture those cameras. We capture those videos and using projective texture to present it on the spherical display. And this actually nowadays can done in the Unity very simple. But before that, we actually wrote this rendering pipeline. And this display allows 300-degree views, whereas the flat display, people can only see from front state. And also because we're using projective texture, so the principle there will always one person can see the correct view, so it can always correct eye gaze. Our next one is the cylindrical display that I have is quite similar to the spherical display, but different from that is we allow multiple users simultaneously to see the correct view. How we do it? This one is we also use the ray of the camera to capture the person, and then we use a ray of the picture to project it on the cylindrical display. With this cylindrical display we created is using special materials, and it can reflect in the it's using similar to the lenticular lens, but we place it vertically so that each projected image have very small viewing zone, so people can see the different view from different angle. And we did a user study to demonstrate it. All cylindrical display can better preserve gaze position for the remote person. And the next display I'm going to talk about is a random hole display. And different from the traditional 3D display is we randomize this barrier so that multiple users from multiple viewpoints at arbitrary location can simultaneously to see what the person or object presented on the display. So, so different from those like a light barrier, we randomize those dots. So there was people at an arbitrary location can see the different pixels, but of course they will lead to some conflict pixels. So we randomize this as a white noise. Here is the results of our random hole display. This was an image, actually the photo taken from different perspectives. So the highlights of our this display is we use a motion parallax as a dominant effect to improve the eye gaze, but also we use a perspective correct view by the stereo view, like people from left eyes and right eyes will see different image, so that we created a stereo view to improve the eye gaze direction as well. The next one is we also found that if we presenting the avatar on the perspective correct view, improves the trust behavior of human beings. Here for this one is we actually developed the model for evaluating trust, because trust is very difficult to measure. It's not like if you say something correctly or you have a right or wrong answer. However, how can we measuring the trust? It's become very difficult questions. If you only give participant a questionnaire, they were rating them. It's not like a very precise answer nowadays. Normally, we need to develop the model. So here we developed the trust model for evaluating this display. I'm going to explain this model here to help people actually using our model to evaluating different like virtual reality displays. We ask the participant very, very difficult questions, like taken from like the Who Wants to Be the Billionaire games. Like we ask, what subject will Bill Gates study at Harvard? Like those questions, people normally don't understand. They were asking from advisors. So we display those advisors on two different types of the displays. One on the flat display and another one is on the spherical display. So people need to trust one person because there was some uncertainty and risk arrived. People was wondering whether the advisors can provide correct answer, like their ability, or will they lie to them, or their motivation was correct. And those kind of the information was normally taken from the interpersonal clues, like if they were looking at the participant. So we found that actually spherical display was have more trust comparing to the flat display when the advisor was presenting on the different type of the display. This is interesting because it's the same advisor just presenting on the different displays with different viewing angles. It will actually alter the people's trust behavior. And for this hardware is very easy to implement, to be honest. We're just using, this is a quite an old system that we use the Kinect to capture the person, and finally using the AR kit and before that it was a software called Face Shift, and then it was bought by the Apple, and then it's used in the AR kit and finally presented on the spherical display. And here is how people actually viewing like different things from different angles. There was people looking at the spherical display and looking at the flat display. We found that spherical display, because participants can always get correct view, it actually improves the trust. So people would like to choose more avatars presented on the spherical display instead of the flat display. Here is the summary is how the benefits of the using spherical display to use in the avatar mediated communication. And all those displays actually a mixed reality display, and it can be situated in the room, or it can be presented on the large museum, so the people around the display can see the different image from different angles. And the next one is display that I'm going to introduce here is a telepresence robot. But it's still actually a display because we're actually projecting an image on the robot face. And we actually found the physical embodiment of a display can actually alter the people's behavior, like alters people's trust. And we compare different kind of the mediate way to communicate different methods. First one, for example, using avatar mediated communication and video mediated communication and robot mediated communication. The avatar mediated communication, like before that, I talked about different way of how to creating avatars, but there always there was like the tracking issues, and also there was uncanny valley exists. So there was a problem in the the avatar mediated communication, but also there was the highlights of the avatar mediated communication. If we created very photorealistic avatars, and it's more easier to present it in 3D comparing to the video mediated communications. And also for the robot, the highlights of using a robot as a way to communicate with people is there was actually a physical embodiment. Like there was actually something standing behind you. It feels different compared to just a video standing behind of you. And also, robots can give you the like handshake or this physical contact, whereas it's impossible for the avatar mediated communication or video mediated communication. And there was another a motion fluency for the robot might be very bad, but there's no problem for the avatar and the video mediated communication. And there were always pros and cons for different type of the ways to communicate with people. The both robot and avatars, they masked out their identities, so people don't know how the remote person is actually looking at. They were just presented by the avatars. For example, if they might be a very old person to present it, while they use a different kind of the avatar to representing themselves, and so people don't know who they are. However, for the video mediated communications, when you see the video, if you know this person, you know this person, and then it's actually providing the more identity clues for while communicate with the people. So as we talk about the different kind of pros and cons for the different type of the communication methods, we actually run an experiment to see which type of the method providing more trust. And here we also use the trust model, advice to use advice seeking behavior under the risk as a trust model, as indicating in that trusting that advisor. We eventually actually found both robot and video achieved a similar level of the trust, which is higher than the avatar mediated communication. And we asked the participant how this might be. And they said that the physical presence of the robot might be compensated of the identity clue for the robot as well. So both the video and robot achieved the similar level of the trust. Both of them performs better than the avatar mediated communication. And another interesting effect that I would like to talk about in the the mixed reality is the leadership effect. This actually we did a lot of experiments relating to it. For example, we created a person in the virtual environment. We can alter the person. This is the physical embodiment things. For example, if you embody yourself into a very senior person to communicate with another person, which which embodied to the like student or the undergrad students. While they will communicate with each other, like the person embodied to the senior person or professor will like become a leader, and they would act like a professor more, even though if they might be both of them was just a student. This kind of psychology studies has happened a lot of time, and we imported one of them into the mixed reality. And here is what we did. We embodied the participant as an avatar in the AR to the AR system. So those avatar was actually presented by the people, and also the AR to the VR body things, and the AR to the VR things, and the AR to the desktop interface. We actually found the person who immersed themselves more, for example, in the AR to the AR thing, both of them was actually in the same co-located location. While they're doing task, there was no bias at all. And also if we embodied our people in the VR things, there was no bias at all. However, if we use the AR to the VR interactions scenarios, we actually found the person in the AR would like to become a leader during the collaboration, like they will talk more, they will guide another person, and also the same things was found to the AR to the desktop communication. Like the person in the immersive environment would like to become a leader, they would like to guide another person to doing the task more, even though they know, even though in the social life they have a similar level of the professionalship. Here's our results. We found the more immersive participant was like to single out as a leader. And we only found the leadership effect for the AR to the desktop scenario and AR to the VR scenario, because it was like they were more immersive in the AR scenario and instead of the desktop, and the VR without the virtual body. However, there was no leadership effect was found in the AR to the VR body, VR scenario with virtual body, and AR to the AR scenario. And we also found the leadership effect only merged out in the 3D interaction, but not for the 2D interactions. This is kind of understandable because if things was presented in the 3D, things can do it more easily in the immersive environment, which also doing things in the 3D as well. And the next display is we actually developed the fake 3D effect is using the adaptive dynamic anamorphism system. The idea of this is like we're rendering one object from one viewing point and rendering rest of things in another viewing point and glue those things together. For example, we render one of the animal from the anamorphic projected image, well, depending on the one user's eye location so that they always see the correct view, while rendering rest of things into the front view, and they glue those together. And these things actually apply to the Disney and California Adventure Park. In one of the Turtles talk, we rendering one of the characters from like a perspective corrected view for one VIP viewer, and render rest of things like fishes around the turtle from other locations. So the one person would always say that the turtle is actually looking at them and talking to them, blinking the eyes to them, feel like different from the rest of the guests. And this is we found that eye gaze is actually improved the engagement and improved the if we're looking at the guest more, if the character was looking at the guest more, they were actually improved the user's engagement, and also the rest of the people, they still have a correct view. Like if the background image render from the normal view, only one of the a small part of the object rendering from the anamorphic view, the rest another person can still see the correct view without sacrificing another guest's viewing experience. So in summary, the words we did like a couple of the display method. For example, display the character in the spherical display, cylindrical display, and also in the random hole display, or presenting those characters on the robotic displays and embody them into the virtual environment. This is like all the methods to display the characters. And we also look at how this actually influenced the human factor of while the user is viewing this display. For example, there was an embodiment, leadership, eye gaze trust, emotion engagement, and also the privacies. And for the avatars, the anonymous feature of the avatars is actually for the privacy is a good thing to use. So here's like a couple of the reference for those papers that I've been talking about, but not all of them, based for the part of them. And thank you very much. This is pretty much it for my talk.
Thank you very much for your excellent talk. And so now I have a few questions about the talk. So about the audio-driven avatar, the audio-driven avatar synthesis or avatar animation. So what is the main difference between this method and those audio-driven 2D talking face driven method, talking face generation methods?
Okay, yeah. So actually, this is a very interesting question because we developed this system based on the 2D in audio-driven methods. Different from the 2D information is that we introduce like a 3D, like the character data set. Because if it's only 2D, when we apply those things into the virtual reality, for example, we use the Unity to apply those characters, we can only see the front view. We cannot see avatars in the 360-degree view. This is one difference. The second difference is for the 2D, like nowadays the 2D audio driver system is most of the work is focuses on the real human instead of the sterilized characters. But our work is developed for the sterilized characters, which have a much more expressive expression, and also it has artistic input for the data sets. Thank you.
Okay, thank you for your answer. And another question is about the display method. So you introduced 4 different kinds of display method. So I'm wondering what display method is used in current VR devices, like in VR glasses or?
Okay, yeah, thanks for the questions. I would like to talk about these methods because it actually applies to the Disney California Adventures Park. The highlights of these things is we allows one user to actually see from the correct view without wearing like those like VR headset. As you can see, like the display that I've been talking about today, most of them is the people don't want wearing a headset in the theme park or in the museum. If they're using virtual reality headset at home, that's fine, but they don't really want to use it while they're having fun at the amusement park. So the display that I'm talking about is glass-free, but people can see it from 3D. It's not a true 3D, it's a fake 3D, but a correct view.
Okay, so
Okay.
so it's technically
yeah, sorry. So, but that Panya, maybe I have a couple of questions as well. So, the first one, can you move your slides to the slides of leadership effects? Something.
Okay. Yes.
Yeah, there's a statement that the last one. Yeah, the next one, maybe the 14th. Yeah, you made a statement that the leadership effect only emerged in 3-dimensional interactions, but not in 3-dimensional interactions. I'm not quite clear about this statement. Can you make more comments on that?
Oh yes, like in the VR, there was like the interaction, like to paint on this spherical sphere, like painting different color on the like for the sphere, and also there was you can using like the ray to selecting those colors, which selecting is a 2D interaction. The surface is a 2D. There was no rotation involved. However, for the 3D interaction means that you actually interact with a 3D object. Like one is interact with like a flat object, flat, like it's like similar to the desktop things. It's interact with the screen. That I called it as a 2D interaction. And while interact with a 3D object, like a sphere, like a cube or different 3D things, I called it a 3D interaction.
Okay, that means that 3D interaction does work, yeah, they all work together. Okay, yeah, thanks. Okay, so another question is about maybe more technically. In your early state of your talk, you mentioned the facial capture. You mentioned that you adopt machine learning to learn the branch shapes for the face expressions as well as the weight. Okay.
Yes.
During how many shapes are there or enough to express facial expressions quite well? So some people use 16, some that. Can you make some comments of that?
Yes, this is like a very technical question, and for our methods is we use a 42 blend shape weight, and we only use a 2-layer, and it works. And when we adapt it to the multiple characters, it's also we use a 2-layer MLP. It works. And for the first machine learning model is for the input, we got lots of data for the blend shape, and also we have a lots of controller value was created by the artist. And we fed this, like we match these pairs each one by one. How we match it is like I talked about from here. Like this slide is talk about how we actually match the like each of the blend shape to each of the controller values. The controller value is very expensive, right? And there's only 44 blend shape weight for the AR kits, and the controller value can be a lot of them for different characters. So this is how we match each of the blend shape weights to the controller values, and then with, based on those matched pair, train the blend shape adaptation models, and finally we use that model to build on top of the AR kit.
Okay, thanks. Okay.
Oh, thank you.
Okay, thanks, Professor Pan and Professor Liu. And next, Professor Liu will give an annual summary of the AsiaGraphics webinar.
Okay, well, so can you hear me? Right?
Yeah.
Okay.
Yeah, I can.
Okay. So thanks, Professor Ri and Professor Pan again for the 2 nice talks at this session of AsiaGraphics webinar. And yeah, just we mentioned this just before the night of Christmas Eve in 2022. And also thank Professor Lan Yi for chairing this session. So as you mentioned before, this is the last session of AsiaGraphics webinar this year. And as you know, the mission of AG webinar aims to showcase exciting research results, inspire and motivate new research, and create a new regular opportunity for the AG community to meet and exchange ideas. And this year, we are very glad to have 20 sessions, each session for 1 month. So with about 25 distinguished speakers for all around the world for this year's AG webinar. And I believe all the audience online, as well as the AG community, have largely benefited from all the talks. And we are very grateful for all the speakers in the session chairs, again, for contributing to AG webinar talks. So all the AG webinar talks will be have been recorded and made available on both YouTube and Bilibili. So for those who missed the talks, you can find and watch the recorded talks in video via AG website. So, so this is my very short summary about this year's AsiaGraphics webinar. So it's time to say goodbye now, and as the New Year's just around the corner, I, on behalf of the AsiaGraphics, wish each of you good health and happy New Year, and also enjoying the holiday season. And see you guys next year. Okay, goodbye.
Okay, bye.
Bye. Yeah, thanks.
Happy holiday. Thank you.
Yeah. Maybe we have some chance to meet in face in the near future. Okay.
I hope so. Thank you.
Okay. So see you. Bye.
Bye.
Bye.